Hey AP Stat, part 2 of 3.2. So we're going to get into that a little more detail about that regression line in this section. So that line, the line we actually do when you do linreg in your calculator, and the most popular linear regression is the least squares regression. It's kind of the nicest one. The formulas work out real nice with it. So there are many different ones we could use to model the association in a particular scatter plot, but a good regression one would make the residuals small, those errors in the vertical distance small. And so we prefer one that minimizes the squared residuals. You could do, similar to standard deviation, you could do like an absolute value, but it turns out the math for that is a nightmare. And it's honestly better to just if you're trying to do minimize of the absolute value of the vertical distances, it's better for like a computer just to kind of like go through a brute force process. Which is where they just compute it for a bunch of different ones and kind of hone in on it. But yeah, so instead, the math works out really nice if we do those squared vertical distances. And we have to do something like that to make those distances. If we just did the sum of them, there's a whole bunch that would add up to 0. A whole bunch of things would make the sum of the distances. So we want kind of the absolute value, or better yet, the squared vertical distances. So that is what we call a least squares regression line. And a little bit of a way of visualizing that is here. If you actually show these little squares, so if I had this vertical distance here, if we square that, you see we can end up with a little bit of an area. We're trying to minimize the area of those little squares that are popping up there. It's just a way of thinking about visualizing it, but really we're minimizing the squared vertical distances. We're trying to make these squared residuals as small as possible. And so if you optimize that, we get a prediction equation. And there's some formulas that we'll look at later that are nice, simple formulas, relatively simple formulas that solve this problem. All right, so we want to make sure we know that the equation we get, when we do linreg, is it actually an appropriate model? And so that's another thing we'll want to do. We're going to look at, see if the pattern is right. So look at the overall pattern for any striking departures from the pattern. A regression line describes the overall pattern of a linear relationship between explanatory variable and response variable. We see departures from this pattern by looking at a residual plot. So you might be able to see departures without looking at this residual plot. You might be able to say like, oh, wow, that graph is definitely curved, or there's these weird outliers, or this weird cluster and things going on like that you might want to describe if it's not just a nice line. But sometimes it'll help a lot to look at a residual plot. And so it's getting to the residuals. It's a scatter plot that displays the residuals on the vertical axis and the explanatory variable on the horizontal axis. So looking at examples, probably the best way to explain this. Here's my original scatter plot. Here's our least squares regression line, our prediction equation. And so we had all of our residuals. Those points were above and below. Well, if we simplify this to just looking at our error, that's what we're looking at here in our residual plot. So we're just looking at how far were those data points from the line. And this is actually a pretty good looking residual plot. What you want to see in a residual plot is that there's no pattern to your error. It actually should just look kind of like a messy cluster of points. It's just like, oh, our errors were high, our errors were low, they're kind of all over the place. There shouldn't be a pattern. If there is a pattern to your residuals, that's a bad sign. That means that there's some feature of the relationship that you're missing. There's some pattern, once you've got your line of best fit, if it fits the data well, there's going to be error left, right? The values are going to vary, but there shouldn't be a pattern to that error. If there's a pattern to it, if these residuals are curving and things like that, that's the problem. And so this is the idea of a residual plot. So notice that like this first point is very close to the line, and that's what we end up with here. This first point is very close to that. So it's kind of like we flattened this line out and just looked at those vertical distances. A couple of points here had some pretty big residuals, so we saw that, and one negative here on this one. Towards the very end, we've got a couple above, a couple below, and so hopefully you can kind of see how those are being graphed. And so you basically plot on your y-axis the residuals, and on your x-axis is just going to stay that. And then the way you do this in your calculator is if you're doing you would have done a scatter plot of list 1, list 2. So you can get a list, create a list of residuals. When you do linear regression, linreg, it actually creates a residual list, and I'll go over this in class. But it creates a residual list that you can plug into to the y value, and so that you're actually plotting your residuals against the miles driven. So the nice thing about a residual plot is that it kind of magnifies the deviations. It really shows you the error. Sometimes the curve is obvious, sometimes it's not so you can actually see, once you do a residual plot, it makes it easier to see if there's any patterns to the error that you may have missed when you just look at the overall plot. And so when you look at your residual plot, you want it to be what I call messy, right? It should show no pattern to the error, and then ideally your residuals are relatively small, like that your errors aren't very, you'd rather those numbers, your distances not be super huge, right? These distances above and below, we'd rather those not be particularly large. Small residuals is good, messy residuals is good. So this is the original data. This pattern is pretty obvious, right? There's this curve to the data, but the way that it shows up here is exaggerated. So where the residual plot really is at its best is when you actually have like a slight curve. You may not notice, it's like, oh, there's a slight curve. You may not notice a slight curve there, but it'll actually show up as a very strong curve once you get to your residual plots. So beware of checking out the residual plots to make sure that the linear model is actually appropriate. To determine whether the regression model is appropriate, look at the residual plot. If there's no leftover curved pattern in the residual plot, then the model is appropriate. If there is a leftover curved pattern in the residual plot, consider using a regression model of a different form. And so we're actually going to do a little bit with it. We're not going to cover all the potential curves because there's a lot of different types of curves, but we're going to cover a few different types of curves in our regression equations and our lines of best fit. If we look back at our actual data here, so we had our data for in the last section for our Ford F-150 Super Cruise. We had a prediction equation for those where we're predicting the price based on the miles driven. We had this like negative sloping line where we had as you drive your vehicle more, the value goes down. We kind of interpreted this. Is the linear model appropriate for these data? So what you would do is look at the residual plot. Is this good? And we want to describe the fact that because there are no obvious pattern in those outliers, there's no pattern left over in the residual plot, the linear model seemed appropriate. There wasn't a better model to fit that data. An exponential or some other type of curved model wouldn't have fit it any better. And that is residual plots for 3.2.